let's look at a few specific things that go into sustainable transportation solutions, right? We had looked at something like this before, but in a different context of how the emissions get determined. In the case of transportation, the greenhouse gas emissions in terms of million tons of CO2 equivalent per year can be calculated as a product of greenhouse gas per unit energy, then energy per unit mile, and then miles traveled per year. So here the primary energy carbon intensity is a question. Whatever type of fossil fuel or fuel cell or electric battery vehicle is being used. This is a measure of efficiency, like fuel efficiency. How many miles do you get per gallon, or how many gallons does it take per mile? The SUVs often talk about gallons per mile as a joke, right? And total demand of travel in your life, a particular user. So in each case, then you can directly see what are needed. So obviously, to increase primary energy carbon intensity, you go for low carbon fuels so that the total emissions per gallon is reduced. Vehicle and transportation efficiency, so the vehicle you are using itself has to get technologically more efficient, and the transportation system itself also has to allow for minimizing vehicle miles traveled and congestion and other things. Maybe mixed use neighborhoods become part of this efficiency as well. Total demand depends on reducing the miles people have to travel with land use and transportation planning. So that's combined there in terms of mixed land use as well, combining residences, offices, malls, shopping, entertainment, etc. So this is the general approach for calculating greenhouse gas emissions from transportation. The good news is that the greenhouse gases from average passenger cars normalized by distance for different regions. You can see here going from South Korea, Mexico, Brazil, India, US, Canada, China, Japan, and so on, have decreased over time, just over the last few decades, and the projections are that this will continue. Okay, remember before we said when you consider the policies and the fuel efficiencies, we are not on target for the 2 degrees centigrade global warming or 1.5 degree global warming. Nonetheless, the planned vehicle technology calls for continued decrease in CO2 emissions in terms of grams of tailpipe emissions of carbon dioxide per kilometer traveled. Okay, here's the fossil fuel consumption. You can look at it as liters per 100 kilometer gasoline equivalent, whatever the fossil fuel or other kind of fuel that is being used. Okay. What is happening with number of electric vehicles being introduced in different regions? We've seen this before in another context. So millions of vehicles in the last decade, going from 2011 to 2019. The Chinese market, as we saw before, is exploding in terms of the number of electric vehicles, and the forecast for the years beyond 2018, when this report was written or when this graph was plotted, is continued increase into 2019. But we have also seen that going out to 2025, 2030, these numbers are expected to continue to increase, but remain a fairly small percentage of the total vehicle market anyways. Okay. And the milestone of 5 million passenger electric vehicles sold would be crossing here in 2019, which happened. So 1 million passengers vehicles, 2 million, 3 million, 4 million out of 5 million. So North America is here in this color, Japan is here, not so big surprisingly, South Korea, tiny, and rest of the world kind of dominates this color here. So they are almost the same here, but actually one of them is here, the green line here. Okay, so you know which countries are dominating the electric vehicles, and this is a kind of a political game under Trump administration, which hopefully is on its way out, even though the drama continues. In terms of thinking about low carbon fuels, fuel utilization for US transportation market in 2018, gasoline is still the majority, 54%. Diesel remains quite high, about 23%, mostly large trucks and some Volkswagen cars and some diesel heavy duty vehicles and so on. Jet fuel, biofuels are about 5%, natural gas is about 3%. As I mentioned in another context before, biofuels are a small percentage, but they are often raised in the context of competing for food grains. Corn ethanol is one thing, and when there was a drought in 2011, I think the loss of corn production in the Midwest created huge problems in terms of diverting corn to animal feed, ethanol, fuel additive ethanol, and then availability for people to consume corn actually. So there is always that context of how food security is going to be affected by the biofuel market. So biofuel is good, but obviously you have to also worry about food security for the vulnerable people in the low income, for example. Okay, so this is for various vehicles produced and vehicle production and disposal, fuel production, and CO2 exhaust emission for a range of life cycle CO2 emissions for different vehicles and fuel types. So life cycle is basically the life cycle of the vehicle itself, production of the fuel, transportation, and fuel efficiency, etc. So this is again in CO2 emissions in grams per kilometer of tailpipe emission. For commercial vehicles, conventional vehicle, battery electric, there is some difference here, they look the same. Okay, renewable electricity and mixed electricity on EU average, and battery vehicle with 100% coal electricity. So different vehicles, same different fuel sources, same vehicle. And you can see that the petrol and coal obviously tend to be very high, whether you look at the vehicle production and disposal. Fuel production, the contribution to the life cycle is what we are talking about, and CO2 exhaust emission. So it's not just the tailpipe emissions that matter when you consider life cycle. You also have to look at the emissions in the production and transportation of the vehicles themselves, and the carbon emission, greenhouse gas emissions during the fuel production that's being used in the vehicle. No question at all that coal electricity is not going to be a good solution for anything anymore, and hopefully coal is basically going to play itself out of the market in terms of the economics, as the old saying that is attributed to a energy minister from Saudi Arabia: the Stone Age didn't come to an end because they ran out of stones, it's just because better alternatives came along. So whenever you think about arguments for divesting from fossil fuel companies or leaving the coal buried underground, the question is, what are the alternatives, especially for developing countries? Okay, that's something that one has to worry about. Cellulosic ethanol comes up in many of these biofuel arguments. Cellulose is important because it constitutes majority of a plant and anything that's used for, let's say, biofuel. In biofuel, you use just the seeds, or in the corn, you just use the corn and not the stalk. All the stalk and the leaves are all cellulose. It's the material that the plants use for the support structure and so on. So if you find a way to extract fuel efficiently out of all that material that is usually discarded, not necessarily a waste, because it can become part of the nutrient cycling if it is left untilled in agricultural land. So tillage practices can leave biomass in the ground and enhance nutrient recycling, carbon content, reduce agricultural emissions, and so on as well. Nonetheless, in the cellulosic ethanol production, this is from Stanford, shows that photosynthesis produces bound cellulose, and then you add acid and do some pre-treatment with heating. You extract cellulose and go through some hydrolysis as opposed to electrolysis, so usually steam and enzymes are involved. Again, heat is involved. Extract glucose, fermentation, there is some CO2 emission, ethanol is produced, and then you add oxygen and combust it, and you produce H2O and CO2. Of course, this is can be a 100% renewable if CO2 is captured and cellulose is produced for biofuel, and somehow the combustion cycle in the life cycle is made carbon neutral. Obviously environmentally friendly, but as of now it is tremendously expensive. There is all kinds of biotechnologies being tried to maybe have synthesized synthetic bacteria that can chew down cellulose and produce directly fermentation and ethanol. Okay, like the bacteria that eat oil spills, for example. Okay, so ultimately life cycle analysis is needed when you go through these arguments, looking at this table of greenhouse gas emissions per kilometer relative to gasoline powered internal combustion engines in the full energy cycle. So actual impacts here could vary considerably, and these estimates just reflect a large number of assumptions and should be treated as illustrative. Okay, so the fuel or feedstock that goes in is listed here, and the percent change with respect to gasoline powered ICEs or internal combustion engine in the full energy cycle for fuel cells using hydrogen from solar, so it's renewable, goes minus 90 to minus 85%. So huge reduction in greenhouse gas emissions. Cellulosic ethanol, expensive, but can reduce from minus 90 to minus 40 in the life cycle, which is very good. Battery electric vehicles, electricity from low carbon sources, minus 60 to minus 25. Hybrid electric vehicles, minus 40 to minus 30. Battery electric vehicles in the current US power mix, minus 40 to minus 20. Diesel itself is biodiesel can be done as well, minus 25 to minus 15. Compressed natural gas from natural gas, minus 20 to 0. Gasoline, of course, is the reference. Battery vehicles with new coal plants would actually increase over gasoline because coal is highly emitting. Okay, so if you combine this information with the previous chapter of distributed energy production, hydrogen resource, fuel cell vehicles, integrating the distribution and production system, and so on, you know that these offer additional levers in sustainable transportation and reducing overall emissions from the transportation sector.